at this point, I hope you see my screen. So first of all, welcome everybody for joining this session. So this is dedicated to training using for optimization methods in CFD. And we're going to use OpenFOAM, of course, but also Dakota, which is another tool for optimization. So also I put some material, let me move here. So I put some material and you should be able to download, but please don't try to follow what I'm doing. So just look at what I'm going to do, what I'm going to say, and then just if you have questions also, and you can post those questions in the chat window, and I will try to address all of them. Every 5 minutes or so, I will try to look at the chat window. And at this point, I think, okay, let me check here. So let me pass here. So at the beginning, I will address a little bit theory. I will bore you a little bit with some theory, okay, something that I need to address, and then we go to the live demonstration. I will show you some examples. So I hope to spend like, I don't know, 20-30 minutes here, probably less, who knows. So let's start first, a brief introduction. So as usual, definition of what is optimization. I guess I don't need to give a definition here, but just to give a general definition, is just the act of getting the best of something under given circumstances. Okay, so basically what we want is just minimize, maximize, or equalize a quantity of interest. So I will use this terminology, quantity of interest, and also key performance indicators, KPI. So this is what we want, okay, subject to some circumstances. So we can apply optimization to any field, okay? It does not necessarily need to be something linked to engineering science, okay? And as I say that, if you can measure that quantity of interest, you can optimize. And this is very important. You should be able to measure that. If you cannot measure, you cannot optimize, okay? So in our case that we're going to do CFD simulations, you need to quantify, to measure that quantity. What you measure is up to you. You can measure anything, okay? To find that optimal solution, there are many methods available, okay? In this training, we're going to explore a few methods, but also we're going to explore a specific tool, which is Dakota. But there are many tools to do that one. You can use Python, MATLAB, whatever. You can write your own solver. They all do the same, okay? The theory is the same, but some of them are easier to use, or you will have some preference. I have a preference for Dakota, and I will show you why do I like to use Dakota. So let's go to the mathematical point of view. So probably I think this is the only questions that are going to show. So mathematically speaking, we can formulate an optimization problem something like this. We have a design vector. So these are your design variables. So if you are doing, it's a geometry that you have, this will represent the constraints that you can control, not your geometry like diameter, length, or the position of the surface nodes. So it's up to you. So this can be a small or large vector. It's up to you, depends how you formulate the problem. Then you set what you want to do, minimize, maximize, equalize, it's up to you. And then you measure that quantity of interest, okay? It can be one or can be multiple quantity of interest. In that case, we talk about a multi-objective optimization. And this problem can be subject to inequalities and equalities that can be linear or non-linear. So linear are quite easy because those represent your bounds or your domain. Non-linear, you need to compute those quantities, okay? It will become another quantity of interest. Later in the live demonstration, we're going to say a little bit about that. So I want to say something about this cell here, the design vector, because this is the one responsible for all the problems that we have in optimization, okay? So this is the one responsible what is known as in optimization, the course of dimensionality. Okay, the larger that this vector is, the more function evaluation that you need to do to construct a good predictor or to find your optimal value. Okay, so to avoid that, there are some other methods. Probably you have fear about the adjoint. There are many ways to do optimization. Here we're going to talk about search methods. Okay. So let me introduce also now some basic concepts. I will use these figures will be 1D, 2D figures. I want to remind you that you can have the problems are multivariate, not necessarily 1D or 2D. So I will use this one just to visualize these concepts, okay? So basically, what we want to do is minimize or maximize whatever we have here. So we can talk about a multimodal or unimodal problem. So unimodal, you have one global minimum. Multimodal, you have different maxima and minima. Okay, it's up to you. Okay, so see that you have different points, and depends how you formulate your problem to what solution you are going to arrive. Then also we can what I mentioned, that the minimum value or maximum value that you are going to arrive depends, okay, from where you start, from your starting point. So see that here you are starting from here, you arrive to this one. Here you are starting from here, you will arrive to this. Okay, so you have to be careful about that. Okay, so you, as in CFD, that you put an initial condition here, you have also starting points. Okay, and the solution that you arrive strongly depends on that. And then also you can bound your problem. So here you see that we have these bounds or constraints. So we have linear and nonlinear constraints. And then we can just force the problem to find this minimum here. And this is important because also when you formulate your problem, you have to be careful, because it can happen that you can over constrain your problem and you will arrive to the solution that you think it is the right solution. Okay, so it's up to you. Okay, this is very open, but you need to formulate problems. It's not something that you press a button or press enter and you launch your simulation and you have it. You need to formulate your problem previously. So let me move here, and now talking about also the some concept that we can talk about single objectives and multi-objectives. So single objectives, you have just one objective function, one quantity of interest. So depending on what you are doing, you can get the global minimum or local maximum, local minimum. But also we have multi-objective optimization. And probably this is what we're going to find when we deal with in engineer science now, because we have multidisciplinary, you know, it's very engineer. It's multidisciplinary, so you have different fields coming together, and most of the time this is what you need to deal. So here, see that this is your quantity of interest, and see that you have two quantities of interest. So in this case, single objective, you are going to have one single solution, or depending how you constrain. But here you don't have a single solution. You are going to have a set of solutions that all of them are equally the same, are equally good solutions, but it's up to you as designer to pick up the best one, or it might be constrained by another field, okay, by another variable. But see that these grid points that you see here, this represents your Pareto front, that is the set of optimal solutions. Then you have here these red points that represent dominated solution. This means that as you move in your design space, you will always get a better solution, up to a point that you find this frontier here that you cannot get any better solution. Okay, so this is the goal: construct this Pareto front. And to construct this is very time consuming, very expensive. There are some solutions also here, the non-feasible solutions. Okay, so it's something like this that in this animation you see better. So see that we start this problem, we bound, we formulate our problem, and at the end of the day, this is what we want to do. So here we're using now derivative-free methods, okay, methods that are iterating, computing this one, and at the end of the day, they will converge to this green line here. This is our Pareto. But as you see, this is just kind of brute force, okay? So this is what is known genetic algorithm. There are many ways to do this one, but the takeaway is it is expensive to compute that. So let me now define, after this basic concept, what is design optimization and design space exploration, okay? So design optimization, we say that it's a convergent iterative process. That is, you start from a point and then you arrive to an optimal solution, okay? You need to formulate that problem, okay? But most of the time you say, okay, this is what I would like to do. But also we have this design space exploration that I like to define it like a divergent iterative process. It is divergent because we're not converging to a solution. We're just exploring. Okay, so this is exploration. And it might happen that while you are exploring, it might happen that you can find that optimal value. But also have in mind that you can use this information just to gather knowledge, extract knowledge from the solution. And honestly, this is the way I like to do it, okay? This is how I like to proceed. Then also we have another way to do optimization, using surrogate-based optimization. So using a design space exploration, like the previous definition, you run an experiment, then you construct a surrogate or a meta model, okay? It's passing through all these points, okay? And I want to remind you that can be multivariate, okay? You can have many variables. And then here you have a mathematical function representing whatever you are doing. And then in this mathematical function, you can use any optimization method at the cost of 0, okay? Remember, this is a mathematical function, the cost is 0. So I really like this method as well. Okay, so usually I proceed like this: design space exploration, surrogate, and then design optimization. Okay, but there are many ways, it's up to you, but these are the major groups that you are going to find in optimization. So here I will skip here a little bit this slide. So this is general knowledge. Oh, okay, just to mention something that usually also you will find some definition called DOE, Design of Experiments. Usually I prefer to use this definition DASE, which means Design Analysis of Computer Experiments. Okay, so it's pretty much the same idea, but usually DOE, Design of Experiments, you use it in physical experiments. So you can measure temperature today here, and then you measure again tomorrow, and they might be different. Instead, computer experiments are deterministic, okay? So whatever you do today here or in another location is the same. But the idea is the same behind that, just to make that definition. So you are going to use this term DAS instead of DOE. So basically, in design space exploration, what you want to do is just to cover your design space, okay? And do a lot of sampling. Also, you want to do that in an economical way. So maybe this might be the best way to do it, but it's very expensive. So there are alternatives, okay? So for instance, this is a Latin hypercube sampling that you explore that one in a uniform, the design space in a uniform way, okay? But there are many ways to do that, okay? And what is interesting that when you do design space exploration, you are just building on knowledge, okay? You have a lot of information. So don't forget this, but that when you have all that data, then you need to extract knowledge, okay? So for that, you can use techniques, data visualization technique, machine learning, statistical analysis, name it like you want. So usually, again, I do all this stuff while I'm running. And very important, you need to do this in real time. You are running your design exploration, doing it in real time, because in real time, it may happen that you can find that optimal value, or you find a trend, a curious trend, or you find outliers. Many times what you are interested in is looking at outliers. So do this, but do it online, okay, while you run. So now that we gave this brief introduction to design space exploration, let's move to gradient-based optimization methods, okay? Now about design optimization. So in design optimization, we have two approaches: gradients or derivative-free methods. So gradient method, they do what it says. They compute gradient information to find that optimal value, okay? To do that, there are many ways, okay? Then we have derivative-free. In derivative-free, we are not computing gradients, okay? It is kind of brute force using different techniques. There are many ways to that one. So this is another way. This is expensive, this is fast, but again, this kind of way to proceed requires a very, very well formulated problem. Instead here, you need to formulate the problem is like kind of brute force, start to put points, and then you get to that value, okay? So these are the two approaches that you have in search optimization methods, okay? So here you have a small matrix that you can use to drive the selection of the method. Now, so see that usually in multi-objective, you need to go with derivative-free methods, okay? There is no other way, or actually you can go using gradient-based methods to construct the Pareto, but it will be more expensive than using the derivative-free, and it's not guaranteed that you are going to have a good Pareto. Okay, so here you have this matrix, but you see that when since it start to get expensive multi-objectives, usually surrogate-based optimization, it is a good approach. But also I want to remind you that if whatever you are doing, whatever you are computing in your CFD simulation, if that is inexpensive, go ahead and use, do not use surrogate-based optimization, use direct methods, okay? So if it is inexpensive, but usually we have seen that CFD is expensive, so we want to reduce that cost, but it's up to you. Okay, so now that I address these basic concepts, and I would like to point out here that to compute the quantity of interest, now at the end of the day, we want to optimize a sensitivity. A sensitivity is that quantity that change in function of your inputs, okay? And there are many ways to compute that sensitivity, okay? So you have seen probably something called the adjoint. I'm not going into details. It's a beautiful technique. It's a different way to compute sensitivities, but at the end of the day, you are going to search the space using any of the methods that we studied. But it's true that the adjoint is very efficient when computing those sensitivities, but it's not always the best solution. Nevertheless, I would like to give you some introduction about this adjoint method, but I want to remind you that this training is not about the adjoint. This is a way to compute sensitivities, okay? We're talking about search methods. So the adjoint basically consists, okay, in CFD, you know, in calculating those, let me go back, computing the sensitivity of the quantity of interest in response to all inputs of the system, everything simultaneously in a single computation. As you see, it's very efficient, okay? And here we don't have any more that problem of the course of dimensionality. So that quantity of interest could be a measure of system performance, stuff like lift, drag, heat flux, total pressure drop, whatever, okay? Whatever you can compute in your CFD simulation. So usually it's something like this, the workflow. You have your CFD solver. You have all inputs that you have in your CFD solver. They are all exposed to the adjoint solver, okay? So we're talking about two different solvers. Your normal CFD solver that we're going to call the primal, and you have your equations. And then after you have your solution and everything coming from the CFD solver, it is exposed, you go to the adjoint solver. The adjoint solver are different equations. So the equations that you have in your primal solver, they must be expressed also in an adjoint way. Okay, there are different approaches also to do this one. So you get the solution, put in your adjoint solver, and then the adjoint solver, you compute your sensitivities according to that quantity that would measure the system performance, okay? So basically what is important here is that here you have sensitivity to the whole mesh. So this is why you see that it's used very often in aerospace applications, that you have the wing and you morph the wing very easy, okay? You have access to everything. Okay, so it's a very nice technique. It's not the solution to all the problems, but it's a very nice technique. So, but just to remind you that you do this one, you compute the sensitivity, but then you need to loop to search the best solution. So this will give you a field, and then you keep looping until you find the best solution. Important to mention also that you need to have the adjoint equations, and also the direct solver or the primal solver boundary conditions, they need to be differentiable as well. So there are many requirements, okay? So not everything that you're going to see in CFD can be expressed as adjoint solver. Okay, I don't want to go into details in that, and there are different ways when it comes to the adjoint solvers now to compute those sensitivities. So you're going to find continuous solvers, discrete solvers, and automatic differentiated solvers, okay? So these are different ways to do it. I'm not going to say which one is the one I like, but in OpenFOAM, you are going to find all these three. So here you have this link. So you have this discrete adjoint, you have the link here. This is the people from Michigan, no, the multidisciplinary design lab. They're doing very nice work. So they have a discrete adjoint. Then also you have algorithmic differentiation. Probably this is the most powerful one, okay, because everything is based in the computer. The computer, it is differentiating everything automatically, but it requires a lot of memory. And then you have the continuous adjoint, is the ESI implementation, okay? So you have those are then implemented. It's all up to you to play around with those. So something that as well related to the adjoint is that usually we do shape morphing, shape optimization. So now also we can do a differentiation of optimization method, but according now to shape morphing. Okay, so let's talk about that. Okay, so we have different methods, okay, to do that shape morphing or geometric optimization. So we can talk about parameter-based or cat-based optimization. This is my preferred way, or you can talk about parameter-free or free-form optimization. Okay, I prefer to do it like this, my personal choice, but it's up to you. In this case, you have access to your CAD application. So you have entirely complete control of whatever you are doing, okay? So this is, for me, is the best one. Then the free-form, you don't have the CAD anymore, but now you default the shape of the geometry, you know, whatever you are doing, okay? So this one will let you have better organic shapes, a little bit more freedom, but you are losing your CAD parameterization. It's up to you, okay? So we can have these two different groups, okay? So let me skip here. Probably you can follow this one. I'm talking about this one. So for instance, this is a case that we're optimizing the wing leg, and see that we have complete control here at the CAD level. So I can control the cant angle, the toe in, toe out, all those angles, the airfoil shape, everything. I have perfect control here. Okay, the only drawback of this one is that you need to do your mesh again. So you have geometry, redo your mesh, but sometimes doing the mesh is not that difficult. Okay, So the other method, the parameter free, okay, is the one that most of the time now is associated with the join, and there is a lot of research going on this. It's not very well mature, but it works, okay? But the idea here is that you have your complete mesh. You need to redo your cap. You just put some control points and you start to push in, push out your geometry, and you get different designs. Okay, you have to be careful that while doing that, it might happen that your mesh will become corrupted, low quality, so you need to go back and remesh. Okay, you have to be careful of that. So usually when using these techniques, the deformation are small, but also you can have large deformation. It's up to you what you do. So now here again we have decision matrix, different methods. Okay, talking about shape optimization. Okay, so let me go back here. So basically we have parameter free, parameter based. Okay, but I want to focus here in the last column here. So usually parameter based, you can use it from the initial design up to the final design to fine tuning. Okay, instead usually parameter free is recommended for fine tuning. Okay, you get a good design and then you fine tune that design using a join or topological optimization. I would like to talk a little bit the CAD tool that I use and why I'm using this one. So there are many CAD tools. I know you have CATIA, SolidWorks, PTC, whatever, ProE, but I like to use this one. OnShape is from the developers of SolidWorks as well, and I like to use it because it's web-based. And the fact that it's web-based and I have access to API means that I can use this tool in any operating system, Windows, Linux, Mac, my Android phone, whatever I move, I can use it. Okay, and this is why I use, because probably you know that all these CAD applications, they don't work in Linux. So if you can take this approach, if you want to take this approach in Linux, it's not possible. You need to do it via Linux, or you need to use very expensive CAD software. So this is why I use OnShape. Okay, it's free. Okay, I recommend it. If you haven't used it, you are missing a lot. It's beautiful. I'm not going into details, and I'm not going to go to do publicity as well. But what I do when I'm doing optimization using OnShape is something that is based in web technology. So you have your client, everything is based using RESTful calls. Okay, so you do a RESTful call of a configuration that you have in your CAD. Go to the OnShape server, go back, and you have your answer. Okay, so everything is done using Python scripting. Okay, so I will show you an application how to do that. I really like, and this is what I'm pushing to do. This is what I do most of the time, this kind. Again, remember that you modify your CAD and then you need to redo your mesh, but you follow good practices, it's not a problem. Okay, so just to move here, and I like to use this slide because we have seen all these methods, different ways to do stuff that you have to be careful also when doing optimization. You need to plan whatever you are doing, okay? So usually this is how I proceed. Now, at the beginning of whatever you are doing, usually your simulations are inexpensive. So what you do there, okay, you manage your resources and you scale out, okay? So you can run 1,000 simulations to get 1,000 results. You get a lot of knowledge, okay? And then you keep moving in your product development life cycle, okay? And when you get to this phase here, okay, you start to scale up by using that join. So you have a lot of knowledge. So see the importance of how you move. You accumulate knowledge when you are sure that you can move to the design phase, okay, here to testing production. Then you start to do those small modifications, fine-tuning, using that join. And for that, you need to also manage your resources. So this is the approach, how I look at this. To final remarks here, just to say that optimization methods guarantee the existence and uniqueness of a global optimal solution. Short answer, no. There is no way to guarantee that. Okay, and you just need to move in your design space, find a better solution, and this is proof. Okay. And what is important that remind you that optimization is very subjective. Okay, so what the method is going to give you not necessarily might be what the designer is looking for. Okay, so you need to formulate a problem. You need to know what you're looking for, and things get a little bit more complicated when you get multidisciplinary. Okay, so when we talk about multidisciplinary, and the classical example is aeronautical industry, like, for instance, you want to reduce drag. So you go to the aerodynamics group, but then this aerodynamic group will give you a design that it will increase lift, reduce drag, for example. But then the structural group will give you an airplane with a larger weight because they need to reinforce the structure. And then this might reduce your payload and handle qualities. And then the flight performance group will complain. And then you go to the sales department and that reduces the revenues. Okay, so you have this loop. Okay, and here we have just 4 departments, but can be very complex. Okay, so this is the problem with multidisciplinary optimization. In any case, at the end of the day, what we want is that our current design iterations should be an improvement of the previous ones. You have that one, it is okay. And also we want to use a sound method, okay, because we don't want to use the what if approach, guessing. You might be the luckiest guy in the world that at the first iteration you get it right, but usually it doesn't happen. So we want to avoid this, the what if approach. Okay, so now just let's talk about the CFD optimization loop. Okay, the big picture. So usually this is the loop that you have, and remember that you can put any application. So you have your optimization loop, you have input parameters, black box application, can be anything, response metrics, and you keep looping. But now if we go to the specific of CFD, it's something like that. Okay, so see that you have a input geometry, input mesh, whatever coupling tool interface, then you have a tool that is going to launch concurrent simulations. Okay, then you have your CAD tool or meshing tool, black box application, get the quantity of interest, compute sensitivities, and see that you can compute it in many ways and keep looping. Okay, so this is how we look in CFD. And as you can guess here, you need to be able to connect all these tools. Okay, so this is something that we're able to do using Dakota. Then if we look at each of these boxes, that when we're running the black box application or the CFD solver, we proceed like this. So see that also here in the optimization, you can go back from here to any of these, okay, boxes here in your vertical approach. But also you have this approach, it's the one that I also like to use, the parallel asynchronous driver. That means that you can launch many simulations at the same time. Okay, so instead of launching a single simulation, you launch many simulations at the same time. So see that here we're exploding our computational resources. Okay, and usually I proceed in this way. I use Dakota because Dakota lets you do this, but also you can implement your interface with no problem. Okay, so here we can talk about loosely coupled approach and strongly coupled approach. In our case, using Dakota and OpenFOAM, we're going to work here, but this doesn't mean that one is better than the other. Okay, it's different ways to couple applications. So see here that we have a list of few open source applications. All these applications that you have seen here, I have been able to couple them using Dakota and even Pythons and other scripts. Okay, and there are many more. It's up to you. Okay, the only thing important is that that application must be able to interact using the command line interface scripting. You cannot have the graphical user interface. That would be a problem. So see that many applications, it's up to you what you connect. So here you have the link, you can see it. So let me move here, and this is, for instance, this is the workflows that I usually use. So see here that in this case we have the famous or infamous Hammett body, now classical case, and see here that I'm connecting all these tools together to do this optimization. Okay, so and everything is orchestrated by Dakota. Okay, so you have Dakota that is optimizer and code coupling, but also manage the concurrent applications. Then I modify my CAD using Onshape. The black box solver, including meshing, is OpenFOAM. Then you measure your quantity of interest, and then here I use Python, Parametric, and JavaScript. I use that JavaScript because I have everything using D3JS and that stuff, you know what it is, that I can control, monitor everything real time. Okay, so I have my server and just log in using HTML5 and I control everything real time. This is very important, real-time data monitoring. So you put that everything and that's all. Okay, and very important then today that data analytics is very important, or machine learning, whatever you want to call it. So always gather data. Okay, because also there is a history hidden now when you are doing that data. So here I would like to call, probably you have read this beautiful report, very nice report, and there are many things there, but this is one of the things that I mentioned, that this is very important, doing things in automatic. Okay, so this is one of the goals, that a single engineer should be able to handle large number of simulations in critical time periods without intervening manually, okay? And this is the importance of getting an automatically foolproof loop of optimization or design exploration loop. So that being said, let me talk about Dakota a little bit. So Dakota, here you have the link. It's a very nice tool. What I'm going to show you is using Dakota version 6.13. I think 2 weeks or 3 weeks ago, they released version 6.14. I recommend you to install because they did a very nice improvement, in particular in the real-time data monitoring. Okay, but pretty much it's a very nice tool, very well documented. Okay, so they have a very nice documentation, so you can visit the link, you can download it. It's open source, it runs in Mac, Windows, Linux. Okay, there is no compatibility problem. So these are the capabilities. As you see, you have all the methods, okay, that you can use. You have it implemented there. But what is really cool that I like is that you have clean interface to Python and MATLAB. If you want to use those optimization methods in MATLAB, you can link Dakota and use that. Even in Python, there is no problem. So the big question, why Dakota? Why not MATLAB, Scilab, or whatever, or R, no, or any optimization method? Basically, it's this, because Dakota has this very nice genetic interface to black box solver. So far, I have been able to connect Dakota to any application CFD. Okay, it is also scalable in parallel computations. We have a very good validation database, fully scriptable. It has this simulation failure capturing capability. So if at any point your simulation crash, you're going to have that report, that log file, and also you will be able to restart for a working simulation state. Have these restart capabilities, and it can be linked to third-party optimization libraries. So these are the main reasons, okay? But by no means I'm just forcing you to use Dakota. If you want to use something else, up to you. So how Dakota works, let me address a little bit, that it will use a single input file. Okay, it's a text file, human readable. So it will look something like this. Okay, so you will have my tutorials, you will see everything, but here's where you formulate your problem. Remember that optimization, design optimization relies in the formulation of a good problem. So here's where you formulate that one. Is you are using design space exploration, the entries are different, but it's very varies. Okay, it's not a big problem. So when you run Dakota, this is how everything will look like. So you have the input file, okay, where you set up your problem, okay, and then Dakota will generate some parameter file. These are the parameter files that goes into your black box solver, in this case in OpenFOAM. So in OpenFOAM, you should be able to identify what are your parametrical variables. So see that you have some template directories. In this template directory is where you are going to insert these parameters, and then you keep running. Okay, so this is a context control here, and here you have this simulator script that can be usually use bash scripting, but it can be anything that you want to use. Okay, so here what you do is just give the sequential steps of what you want to do. So usually in OpenFOAM you go block mesh, snappy X mesh, icophone, and post processing. So you put your steps and everything here. So this is what is happening. Get your output and keep looping. Okay, so that is how it works. So that is a little bit about documentation. So at this point, I will go to some examples, but before talking about that and the live demonstration, let me see if there are some questions here. Okay, so there's one question. Yes, on Shape is free. It has two licenses, free and professional. The free license has the same capabilities as the professional. So yes, in the university, we use that one to teach here at the University of Genoa, and located in Genoa, and it's free for students and have the same capabilities. And then you have the professional, where I guess you have customer support and that stuff. So I don't see any more questions here. So I will move, give a minute, okay, press here. So now I will move to show you a few examples and then to the live demonstration. So these are actual examples that we have run. So these are illustrative examples, okay? They are not very, well, there's one that is kind of advanced. So this is a case that I like to use just to show at the beginners. So see that you have this geometry, 4 design variables, okay? And what we want to do is minimize drag. Okay, if you don't put any constraint here, basically this geometry is going to disappear. okay, zero drag. But we put some constraints. So see that in this case, we are over constraining this problem to get to a specific shape. So we want to measure efficiency. So we formulate a problem. So we have here these lines that you can read later. Okay, so we're going to use all the methods that we talk about. So the first one is gradient-based method. So remember that gradient-based depends on formulating your problem. Okay, starting point, gradient, step size, the method, everything. So see that in this case, we over constrained the problem and see that starting from this is the starting point. See that we get to this geometry. Okay, but this is over constrained. So this is the best case, the best drag reduction. Okay. 15 function evaluations. Remember that there are gradient evaluations that I'm not showing here, but in total it's like 30 cases. So you see that this problem in about 10 minutes, but this is an old computer, probably use the one that I have today will be 3 minutes. We managed to get this using gradient information. Okay, so see that how it is evolving. As here you can see clearly, whatever solution you get depends of how you formulate your problem. Then using design space exploration, you just run random experiments, but it's not random, like whatever you want. There is some logic behind, there is some theory. So see that now we start to analyze the data, look the distributions of the data because you want a unit for sampling. So this is why you have here the histograms. Then you plot the quantity of interest and see here that you have the response here, and then you can construct here regressions model using this, or you can identify easily outliers. Many times I'm focusing on outliers. Okay, so now you can analyze this data. So see here that you have the correlation, the correlation matrix. Okay, so here these values are close to 1, means that that is a very important quantity that you cannot neglect. Instead, if the values are close to 0, there is no clear correlation. So maybe you can neglect that value, that quantity. So all this stuff, you can use it. You can call it whatever you want, machine learning, statistical learning, whatever. Okay, so you can use these methods to construct models and everything. And I like to use this one, not box plot, to identify outliers. So in this particular case, see that I have these outliers, and then you can go and see what is happening there. So there are many things to do. Okay, and this is why I mentioned important. Do this, but do it real time. Okay, don't wait until the last simulation to do it, because real time you will identify immediately many behaviors. Okay, probably in this case I like this slide because here we have original data, tidy data, meaning the clean data. For the train eye, you will realize that there is this funny behavior here. So see that this is what running online. I realized that there was something wrong in the simulation in my case setup. Then I analyzed my case while it was running. Okay, I arrived to the conclusion that I don't need to restart. I just clean my data. So this is important, monitoring real time. Then you can go construct surrogate models. So in this case, this is how the Kriging interpolation looks like. I'm not going into details. And you can optimize at the level of the surrogate model. Okay, so there are many things that you can do. So for instance, the same case using that joint. Okay, so see that, and very important also when you do optimization, in particular a joint, try to avoid unsteady solutions, okay? Because every single state of your unsteady solution will correspond to a different shape, okay? So in this case, see that at the beginning it is unsteady and that is a problem. But then see that after 15 iterations, we're getting to this, okay, it's evolving. And at the end of the day, after kind of 40 iterations, we get to this shape. Have in mind that to get to this one, I have to remesh, smooth the surface mesh. Okay, but we get to something similar to the gradient method. Okay, so this is also to disprove a little bit that the adjoint is the absolute best method. In this case, it arrived, but it requires a lot of user intervention. Just to mention that, all these methods are valid. So now let me move to something similar, Dagger board, shape, optimization. So this is the case, the Dagger board here. So we have 12 design variables. This is multi-objective, by the way, one nonlinear constraint. Okay, so as you see, there is a lot going on here. So in this case, we decide to use design space exploration, surrogate-based optimization. Okay, this is how it works. And see that here we have our DAS experiment, 750 experiments, and the MOGA. Okay, 1500, all of the twice this one. Okay, so this one we got this exactly the same Pareto, but we save time here. Okay, so here we have our correlation matrix. Okay, everything. And what is interesting is I mentioned that by using surrogate-based optimization with 700 experiments, we managed to get the same Pareto as the one we got using the MOGA, okay, without using meta models. And then, well, again, you just explore your data, interrogate your data. So this is another graphing technique I like to use, the parallel coordinate. This is just to interrogate multivariate data, and you can see the influence of all variables. Any case, so at the end of the day, see that in this case we have many solutions. Okay, that Pareto and every single of these dagger boards, it is a good one. It's up to you as designer to pick up the best one. By the way, some timing about this one, this was very inexpensive. You might think that, okay, there were like 1,500 simulations. This running with 32 cores, it took like 3 days to do this one. So very affordable. The measures were about 2 million cells. So it's very affordable, okay, as you can see. So just to mention again, another case, the bulbous bowl shape optimization. So in this case, we're using the free-form deformation and surrogate-based optimization. So this is our problem, and we construct our surrogate and stuff that interesting to look that sometimes see here that we have two optimal values. Okay, it's talking about multimodal functions. Okay, so if you start from here, you might get to this optimal, or you might get to this one. Okay, but it's important that is you use directly a gradient-based method. You are looking to this, and you don't know what is happening in your design space. Instead, when you construct these meta models, now you can exploit your design space. You know what is happening. So these are why I like to use these techniques. Okay, so I will skip a little bit here. You can later read. Also talking about that, you need to also monitor a lot of data. Do not look only at that quantity of interest. Also, like here we have the key performance indicator, that is the resistance. But then if we plot histograms of resistance in the surface, you have a different story, or you can have a better explanation why this is better than the other. And talking about also monitoring data real time, look at that. We implement this method here by looking at the data and see here that we're computing excuseness of this signal. So see that very interesting. While running, we found here that we have this excuseness, and immediately what we did, we go back, we look at the dictionaries, and we identify that the problem of that excuseness, it was the order of accuracy of the tolerance model. Then we change it and see that now we reduce excuseness. Stuff like that you can implement it, and real time you can just implement corrections. Then another case that I would show you that this is lately I'm doing, and I really like this approach because here, so far you use the quantity of interest and you use, you measure like drag leaf. But in this case, what we're doing is that using image similarity or image recognition or segmentation to do the optimization. So what we did is that we have a given distribution of the velocity at the outlet. So now let's do the optimization. In this case, we're changing this angle, but you can do whatever you want to get a given velocity distribution. Okay, so this is more sound than using stuff like the, distortion coefficient, uniformity index. Okay, it will give you a better results. And I would like to digress a little bit from the presentation just to show you this and why it is important to visualize the data. Now, this is the famous Datasaurus, something similar to the Ascon quartet. Look at here that you have different distribution, but each one you have similar descriptive statistics. Okay, and this case, what you see here might happen here. Honestly, it had happened to me. Sometimes doing something and I get external results, and then I realize that you can have that exactly the same situation that you see here. You can have same descriptive statistics for different distributions. So this is the importance of also visualize your data. And this is what we're pushing now, why I'm pushing more to do this one. So we visualize, but also we compute some quantities. So in this case, see that we have a target distribution, this one. We have our cat change just the pi angle of the pipe, the inlet pipe angle, and then see that by using this criterion, the similarity index, we see that the closer this number is to 1, the better it is. So see here that we have our optimal value here. By using entirely techniques using in the computer image field. Okay, there are different techniques: segmentation, similarity, object identification. In this case is similarity we're using. Then design optimization compared with also a method of design space exploration. and again, some multivariate parallel coordinates. And the final case before going to the live demonstration, and okay, a little bit over time what I was expecting. So we have this is the last case that I'm going to show you a Formula One car. So here we're optimizing, actually we're optimizing the whole car. We're using the last technical regulation for the next year. For in this case, we work just in the front wing and the wheel. Everything we design it from scratch, okay, using all these regulations. So as you see, we use on shape, we have complete control of our geometry. So I will show you some results that might seem strange for you, but there are some logic behind all the choices. But we received a lot of support from Marco Giacchi. He is a leading expert in this field, and he was just giving us guidelines how to do this. So the idea is that when you read the technical regulations, you can design your front wing, whatever, and then also see this blue box here. This is your constraint, your geometrical constraint. And basically your design cannot be outside this box. So this is a huge constraint because it's clear that Formula One, we want to maximize the downforce. So you will see, okay, let me increase the angle. But when you start to put those constraints, it's not much you can do. Okay, so every 1-2% you gain, it worth a while. So basically, we run this case using that joint and see that that joint will give you, this is what is called now the design velocity vector. So basically, it's telling you where you need to push out your geometry to increase, maximize the downforce in this case. Here you have the comparison, case-based, and then the best case using design space exploration. Okay, I'm not showing here the case after we pass an adjoint, but here we have the data, the quantitative data, and see that this is the base case. By the way, this is percentage error that we're plotting here, everything reference with this case, and see that you have different outcomes here, and these two that you see. So the green one is the best case from the design space exploration, and the orange one is the best one for an adjoint. See that one adjoint solution, they managed to increase a little bit downforce, but it was really bad in drag force. This one increased a lot, but also, no, sorry, this decreased drag force, this increased a lot the drag force, okay? So see that, again, it's very subjective. And then when we were consulting with this Marco Giacchi, he tells us that this makes sense because it may happen in Formula One that you can use this wing for instance, a slow track, okay? You want a lot of downforce in a slow track, and this one would be for a fast track, okay? So depending on what you're doing, but see that absolutely that joint didn't give the best solution. And by the way, to get this two adjoint solution, there were many iterations because the deformation proposed by the adjoint was too much. So we were a little bit outside those requirements that I show you. But also when doing this, and also we check at this vortex. So see that we have a vortex here, and we want also to shift the location of this vortex outwards, okay? Because then when you put here your car, the monocoque structures, it may happen that this vortex goes below, and that can cause problems. So we want to shift it outward. So also there is not only downforce, also here we have this vortex. And here was important to use design space exploration because the adjoint is not very easy to implement, how to do this optimization based, for instance, total pressure, whatever. Well, some visualization here, okay, Q criterion. And by the way, just to mention that this adjoint computation is not done using OpenFOAM, but now we're moving to compute it using OpenFOAM, and we're just talking with we have a collaboration with Eric Shaper, and just to show you what they have done, that they have this Porsche, but now we're passing this geometry to them, and we're going to do exactly the same in OpenFOAM and to see if we get similar results. Okay, so this was all. These were all the cases that I want to show you. Now let me move to the live demonstration. Okay, so in the meantime, just let me see if there are any questions in the queue. For plotting, yeah, now Dakota, as I mentioned, the version 6.14, they have very nice tools to visualize the data, but usually I have my scripts using D3.js. So I use JavaScript D3.js to do everything interactive using HTML. given a sensitivity solver in OpenFOAM, which computes sensitivity, how to process. Yeah, yes. When we run the case, the tutorial, you will see. But yeah, you need to compute. Doesn't matter the solver you use. Somehow you need to convert the data coming from the solver to the data that Dakota likes. So Dakota will take a input text file, and then you need just to put it in the format. But you need to do that data manipulation. Usually use Bash scripting or Python. So when we run the tutorials, we're going to see that. Are there dedicated functions objects? Not to my knowledge. You can implement that. Yeah, you can use any function object. You just need to manipulate your data. I'm interested to know the marriage between OpenFOAM and Dakota. Okay, I guess it was a common. Yeah, for the Formula one, we use Fluent. Now we're going to move to OpenFOAM. Okay, so hopefully in a few weeks we're going to have results. So now let's move to the tutorials. So my advice is just see what I'm going to do. If you have questions, please feel free to ask me. So if you download the cases, likely you will have this folder. So let me move here. So I'm working in my computer. So you're going to have the folder, and you have these three cases. So we have the cavity case. We have this should be on-shade. This is using on-shade. This is the one with image recognition. And then the blown body, the one we saw. So I will propose to start with cavity, okay? So this is a classical driven cavity case that I hope you're familiar. And I want to show you something because many people say that, what is the idea of doing this? This is a stupid case. So basically what we're doing, our problem formulation is this one, the driven cavity that you are familiar, and what formulating is, I want to maximize the pressure here in the middle of the cavity, okay? And my design variable is the velocity here. So here I'm not showing now the complete formulation, but usually we go from negative to positive values. And usually people immediately say, what is the sense of using negative values? Should the problem be symmetric? And actually, the problem is not symmetric. Okay, so sometimes, you know, don't go and drive and draw conclusions. Okay, and so many people start to become puzzled by this. But the equations are invariant, but the problem here is how we're measuring. Okay, so how we're measuring the pressure distribution is not symmetric. And I like to say here that this problem might seem stupid, but you can get it very complicated. So for instance, I can ask you, try to use the adjoint to reduce or to suppress recirculation areas, or use a gradient search method to suppress recirculation areas, or try to optimize the problem to get in the sampling point a symmetrical distribution. And it's very complicated, okay? It's not straightforward. So you have this problem that is super fast that you're going to see, but you can test all these concepts. By the way, to suppress, for instance, to suppress the recirculation zones that we don't see here, we're using image segmentation. So we have algorithm, image segmentation, identify this one, then we have fully parametric geometry, and then we reduce that. So as you see, there are many approaches to do that. So as you go here, I will propose to start, or I will show you first the cavity vector parametric. So this is the parametric case. So basically it will be just changing the design variable, which is velocity in the top, from -2 to 3. That's all. But here we're going to understand how to set up everything. So what is important also, I want to remind you this figure, how Dakota works. This one. Okay, this is important. Okay, so go back to the figure. So see that when we run Dakota, we have a template directory. In this template directory, you put your template files, the variables that you know you're going to change. So that here can be any file. So in this case, it's velocity. So see that U template, I will open here for you. And see that my parametrical variable is this one, the name of the variable, and see that I put it into curly braces, okay? So you can change the delimiter, but I already checked that in OpenFOAM, you are not going to have conflict using curly braces, but you can change it. If you want to use double curly braces, square brackets, whatever, you can change it. But see that I'm naming my variable x1, and now Dakota automatically will replace this. When replace that variable, then it will copy that variable into your case directory, and then you launch your cases sequentially. Okay, so here, one design variable. This is the case base, the one that I know is working. Okay, so you set up, you are sure, 100% sure that this one is working. You have all your monitors, function objects, the sampling, everything here. Case definition, Dakota case in. This is where you define your case. So if I go here, see that I'm not going into details, go to the documentation, it's very well explained there, but see that here we're defining our problem, okay, using this method. See that the name of the design variable I'm giving here. So the design, I have one design variable and it's called X1. You can give any name, avoid spaces, okay, or funny characters that are no question mark and stuff like that. But you give the name here. So if you have 3 design variables, you put here and then you add more design variables here. Okay, it's up to you. Okay. Then here, see that this is the interface. So Dakota have many interface. This is the one I recommend you to use, the fork interface. Then asynchronous means that Dakota will launch, you will give Dakota the capability to launch many simulations at the same time. See here that in my case, I have 4 cores. I'm telling that launch 4 simulations at the same time. Okay, by the way, the simulations can be in parallel. Okay, so in this case, the OpenFOAM are in serial, but you can put the compose part, everything can be in parallel. Okay, you need to know your resources. And see that here you are telling that my template files, the files that I'm going to change are located here, template there. See? And that's all. Then this is a copy and paste. I have just one objective function. I don't have gradients or Hessians, okay, because this is a vector parametric. And that's all. Then the next script, that is, you look at here that you have analysis driver. This is the program that you want to run. Okay, so this is a bash script where you put all your instructions. So let me go here and I will open this. And you will see here that these are the steps that you use to run OpenFOAM or whatever. Okay, I also use it very often with Fluent. Put your steps there and that's all. So see that copy your case base, the one that you know is running, into your current directory. I will clarify what is a current directory when we run. Then here you are doing this manipulation. This is I think a pair or Python script, I don't recall. This is the one that is doing the data substitution. It's opening the file and it's substituting the variable that Dakota is proposing. And it will save it with this name. Here I just substitute. And actually you can put it like this, okay? But it's up to you. I like to work like this. Copying to 0 because this is the OpenFOAM structure, and then just set up your cases. Okay, run, do the sampling, and then talking about how do you get the output of the solver. Here you have, this script is divided in 3 parts. See the analysis. Okay, first you have preprocessing, analysis, and post-processing. In post-processing, you need to convert the data that you are sampling into the format that Dakota likes. Okay, so here I'm doing this data manipulation. So I usually use bash script or Python to do it. Okay, so it's a very specific format. Okay, when we run, I will show you. And that's all. When you have this, Dakota will keep iterating. So I will go open my terminal here. Okay, and I go Dakota. Okay, just to run also, you type Dakota -I and the name of the input file, which is this one, okay? And that's all. Then you can also save, you can save the output, whatever. You have a README script there and you can read it to see that. So see that I launch it. And now Dakota is launching everything, and see that you have here. Okay, it's a very fast case. Okay, but when I talk about current directory, it's this one. See that Dakota create workdir 1, 2, 3. All the information is saved here. So now as you go back to the simulator script, probably you will understand better the steps. So see that what I'm doing here, when you enter here in this block, analysis block, you are already in the working directory. So here is where you start to copy and move files. So see that I know that I am inside workdir.1. So copy file, the base case, see that you go one directory back, copy this one here, copy this one, into 0 because this one I already have it in my working directory, and that's all. Okay. So this naming that you see here, workdir.123, it comes from here. Okay, so you see here, see that I'm telling here, save everything and name order. If you don't want to save this one, just comment this one. But I recommend you just to keep it here. So see that you have the solutions, and then you can parameterize ParaView to create your figures and everything. Okay, so this is how it works. So also to open here, see here that you have this file, results out. This is the file that Dakota will read to keep looping. It's called results out, see here, because see that result file, results out. You can give any name. I usually call it like this, results out, panels in. Usually this is recommended by the developers. So here, this file, you need to format this in the specific format of Dakota. So basically see that what you do is just put the value there. So for instance, if you are running a multi-objective optimization case and you have two quantity of interest, quantity of interest 1, quantity of interest 2. If you have a linear constraint, linear, non-linear constraint. If you have gradients, gradients. If you have Hessians, Hessians. So this is the format of this file. First, objective functions or quantity of interest, then non-linear constraints, then gradients, then Hessians. This you need to do it. Okay, this is the user responsibility. Usually it's relatively easy to do it. Okay, but again, people will start, oh, but by simulation it is unsteady. Well, in your script, implement a small, I don't know, function to compute the average of the last 300 iterations, whatever. It is up to you, but this is your responsibility. To set up this one, it is relatively easy. So as you enter into each folder, you will see that it's exactly the same data structure. Okay, so this is it. This is how you couple, and you can put as many applications as you like. Then finally, you see your screen, you see that you have here some information, grading, whatever. Okay, so you can save that also to a log file. But also you will have this file here called table out. If I open this one, here you are going to have your solution. Okay, so see evaluation ID, the number, the value of the design variable, your objective function. Okay. So in this case, I don't know, I modified something. I didn't compute it. Okay, it's strange. I will check that one. Yeah, I was playing with this case, but see that you have your output. It's called table out.dat because, again, if I go back to the Dakota case in at the beginning, see that I'm calling this file like this. Okay, so it's relatively straightforward. Just get familiar. I invite you to play with these cases that are super easy. Okay, so this was the vector parametric. So let me move, and now I will propose another case. Okay, so let me move to the gradient-based case. Okay, cavity gradient based. Data structure is exactly the same. What it will change is the method. So if I open the file, see that now the method here is a different method. There you have many methods implemented in Dakota, and again you can interface Dakota with MATLAB, Python, Gurubi, whatever you want. Okay, there is no limitation. Formulate your problems. You can have inequalities. You have an example there. Everything here is exactly the same. Now in response, see that we have one response, but also we have gradients. Okay, we're doing search using gradients. So you need to tell Dakota how to compute those gradients. Okay, and usually we compute it using a numerical method. Now, so what Dakota will do is will perturbate the case what is running to compute gradients, and that's all. And again, you need to give information and step size. Sometimes the problem can be very sensitive. Okay, and here as we're converging to a solution, previous case it was if we were not converging to a solution. Here, yes, you need to give a sense to what you are doing. So see that I want to maximize. If you want to minimize, you put minimize. If you have multiple variables, you are going to put second minimize, third maximize. You put it like this. Okay, so that's all. By default, if you don't give anything, by default, Dakota will always minimize. And comments are you use the hashtag or pound numeral, whatever. So this is how you set this case. So let me run this one. Okay. Again, it's running asynchronous. So remember that now in asynchronous, when you run gradients, the maximum number of functions or evaluations that you can do is the number of gradients that you can compute at the same time. So for instance, you have 4 design variables, you cannot do more than 4 gradient evaluations, okay? You have 4 variables, so you cannot do. Instead, when you do design space exploration, there is no limitation in the maximum number of function evaluations. So I will run this one. Okay, now let me get out. Okay, CD cavity gradient C1 and okay. So see that super fast. Okay, now it's giving you here the output, but also I mess around with something here. Okay, 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 I think I need to load Dakota. So it is not running. Oh, okay, so. Also, yeah, I'm using Python. I forgot, so I will load Python also. So I need to load Python. So the previous one also. Yeah, Dakota. Okay, let me do clean. So yeah, also when doing this one, you need to load all your environment variables. So in this case, I also have Python. Okay, I need to load OpenFOAM. Okay, now it's running. See, I forgot that I have that. So I don't know where I have the Python script. So see that in this case, using this method, and as you open here, see that you have all your function evaluations, everything. Okay, so here you can enter and you can see the history of what was happening. Usually you open table out. Here you will have only the function evaluations, okay? You don't have the gradient evaluations. You will need to get it from the screen, not from the terminal, or you can save the log file. But this is just function evaluation without gradient evaluation. So see that starting from here, your optimal velocity to maximize the pressure in the middle is this one. So as you compare with the other case, now the vector parametric, you will see that you have that one. Actually, now this is the solution. Now, gradient vector parametric. Okay. So actually, I think I have here in solutions. I put already a few solutions there. So if I go here, let me open to see to plot that. So let me use new plot. So there you will have the solution using different methods. So you have nonlinear squares, surrogate-based optimization, using SOGA, single objective genetic algorithm, MOGA, multi-objective genetic algorithm. So I will go to this one to show you how to formulate multiple variables. But in any case, so for instance, so see here the comparison, vector parametric, and then the gradient method. So see that the gradient method start from here, it converges to the maximum value, the optimized value. But why I say that it doesn't give you any information of your design space. Instead, design space exploration, see that it gives you more information. So now you can create your meta model. Okay. So there you have, let me plot this one. So for instance, so this will be the multi-objective case. So here I have different populations. Also, this case is saving how the population or how it's evolving the population, and you see your design space. I know you can later analyze what is happening here, but basically your optimal solution is there. So let me see. Okay, is there any questions here? So do you have an example of real time? Okay, maybe I would put, yeah, I have many examples to do the real-time stuff. I have many scripts, so probably I can tweak something later. Okay, do you have, yes, you have access to the test cases. Okay, you have also here in the chat, here in the conference room, you have access to all the cases. Yes, you don't want to save the work directories, just comment that word, but I don't recommend you to not save those directories, okay? Well, yes, you have large cases, you're going to save a lot of data. So now let me move to the MOGA that I want to show you how to set up this case. And actually, in my case, the MOGA, okay, let me move cavity MOGA. Okay, so the MOGA is not, there is not much different, okay? The only thing is that if I go here, open Dakota case. So see that now you choose the MOGA. Again, I'm not going into details about the method, the multi-objective genetic algorithm. Okay, the theory is wide on that. So there are many options to control that. Okay, so I put in here a few of the options, but many options. Formulate your problem. And now see that you have number of objective functions, 2. Maximize the first one, minimize the second one. Okay, so that is the difference. But then also when you go to the simulator script, it's pretty much the same. So see that now I have 3 parametrical variables. So see that all these 3 dictionaries, I'm doing substitution. So I'm doing in velocity, pressure, and also viscosity. And remember, at the end also, you need to manipulate your file to get your data in this specific format. So in this case, I'm doing using these bash commands. So I'm using AWK. Just basically my second quantity of interest is the square of the pressure. Okay, so but this is your responsibility. So see that by using these simple commands, you can do very crazy stuff. Okay, so and if it is not enough, you can use Python or MATLAB. There is no problem. Okay, so let me run this case also to show you, because this case is very time consuming in the sense that it will run a lot of simulations. Okay, so if I go now, Dakota, so if I run this case, see that it's running 4 simulations at the same time, by the way, as you look. But as it is a brute force method, it will run a lot of function evaluations. Okay, so this is the problem with multi-objective optimization. Now that you need to use these derivative-free methods that they often compute a lot of function evaluations. Okay, so again, you can control also the maximum number of evaluations, everything. But at the end of the day, it will generate a file where you have the Pareto. Okay, so the difference here, so see that also is saving the populations, everything. Okay, the difference here that now your Pareto, you are going to find it, you will find a file here called final data. In that final data file, you are going to have your Pareto. So I will let it run, and I will stop here with this case because I'm running out of time. I want to show you another one. So then you have different formulations there. You can do it at your own pace later. So I will skip the blunt body, or probably let me show you a little bit. The blunt body is pretty much the same, but here where I'm using to do the geometry and the mesh, I'm using Salome platform. I know you know this tool. So again, you see that you can use any tool. So just to show you the workflow. So let me go here, and actually, as you see, it's pretty much the same, but as you open simulator script, see that now here, I'm calling Salome. Okay, so if you are planning to run this case, be careful that this is where in my computer I have Salome installed. Okay, you need to change the location, and also you need to use Python. So see that you just call that one, and in this case, Salome, it will use a Python script, and this is the parametrical variable. Okay, so as you go into template here, see here that you have the parametrical variable there. So as you rig this script, somewhere you're going to find that you have these curly braces that are controlling. Now see here that the same variable x1, x2, x3 is controlling the geometry using Bezier curve. Okay, so as you see, pretty much there is no limitation what you can do. If the application can interact using the command lines interface or input-output files, as I say, there is no limitation. Also, you must be able to measure that quantity, okay? So that's all. You can run this case. Okay, it should run clean. Dakota is a nice tool. It has some problems. I'm not going to comment into that because to run it use ports, no? And sometimes those ports are busy and then it will get stalled. I'm not going to comment on that, but I would like to move to the last case. Now, the static mixer, the one that we're using now on shape, and we're using also image recognition. And I will do something here, okay? Let me go. I will launch that case. I have another computer where I have many processors. So I will launch 5 simulations at the same time using 8 cores. So you see, just to show you that you can scale with no problem. So this should be very fast in this computer. Okay, so a static mixer configurations, simulations. Okay, so this one use Python 2, be careful. And this one you need to load Python 2, F8. And while I explain you this case, how it works, I will let it run. So see here that it's launching 4 simulations at the same time, or 5, sorry, 5, and each one is running with 8 processors, okay? So that should be fast, and let me now explain you this case, what we have here, okay? So I will close here. So first here, you have this static mixer outlet this is where we have the image similarity script. Now, so this is a Python script that using this in comparing, okay? So we test the program, we have it here. So basically what we do is target image, and this is the output from OpenFOAM. Again, I have this script also in Python in ParaView. So I'm running ParaView in batch mode. You have PB batch. You get this one. So you need to have all the right tools. By the way, if you are running in a cluster, you need to install ParaView in headless mode. So since that you have to be careful, okay, but in your workstation should work fine. So basically what it will do is just compare image and will give you this similarity index, and that will be your quantity of interest, okay? So if I enter, for instance, let me enter here in this case. So here I will show you how it runs. So let me go here. So first I generated the geometry using Onshape, okay? I will show you the geometry. By the way, you have the link there, so you can also get access to this geometry. You cannot modify, but you can copy and then you can modify the geometry. Okay. Okay, it seems that I have a problem there. Let me go to this one. Okay. I don't know what is loading, but I just wanted to show you geometry. It's the static mixer. But in any case, to show you how it works. So basically, see that we have here support files. So here we have this is it Onshape API. I'm not going into details about that, but just to mention that you have a developer portal where you have access to the API and you can program that one. You will get the instructions. It's a Python API. So we have access to that, and then we can do the calls. Also, to use this script, you need to create these credentials, okay? So in the files that you have my credentials, this one. I will erase that later, but you just create here a new API, and it will give you the credentials. Select these 4. You can select everything, but you don't want to purchase anything. And you create an API. And this is the information that you use. Okay, see that you have access key and secret key. Okay, you can erase that later. So basically this works like this. See here that you have this file. This is where you put your credentials. You need to generate your credentials, put it there. Then you have these specific scripts that are going to do something in particular. So this one is just saving the STL files because Snappy works with STLs, and also is changing a variable in my design. You have your design, I have access to that specific variable configuration. So that is what it's doing, okay? So this script is fully parametric. It works in the same way as the previous case. You put the curly braces and it will generate all the new geometry. So let me show you, let me run this one. Okay, so this case, a static mixer configuration geometry, it will only generate the geometries. Okay, so you need to load, remember, Anaconda 2. And then I go, I don't need open from here, I go like this. And see that. Okay, I have a problem with my. Okay, yeah, I need to update the keywords. Okay, let me clean up this one. So I go here, let me update the keywords because these are all keywords, if I will recall. Yes, yeah, those are all. So. Okay, I updated my keywords. Let me run here. Okay, now it's running, it's communicating with the Onshape server. Remember, this is completely free, okay? And as you enter here, what you have, you're going to find there the STL files, okay? That has been modified using this script, that's all. So see here that you have the STL, I gave it the test STL. Okay, you will need to open these files. You will see that there and telling save this file with this name. But you have the STL files. Now you get the idea that if you want to do your loop, optimization loop, you go here, you have exactly the same, but doing with Snappy X-Mesh. And here directly doing the simulations. Okay, so let me go here. And if I open simulator script, see here all the steps. So see that this is my parametrical variable. This is where I'm changing the configurations of my geometry, okay? So this is specific how those Python scripts work. See here that I'm moving files, okay? I know I have my files here, there, and now here you just put your steps to run the simulation, okay? Then this is important. As I mentioned, I'm using PB batch to save the file. So you need to have this, you need to load that library to have PB batch. And then here is where I do the comparison, the structural similarity image, and then output, okay? The simulation, here you have the run all, and that's all. There is always a question, but how do you guarantee that the name of the patches is always the same? That is up to you, that you need to do the script. But here you have these patches, is where I'm doing the renaming. I know how, when I save my STLs, I use a specific utility to split everything in different surfaces. So you start to do the renaming. So this is stuff that you need to do in automatic. You need to implement that, okay? So after you run that, and here, if I go back to my computer, it is done, okay? So all the simulations, you enter here, you see that you have all the, see that it's running in parallel, and see that basically ParaView is saving these screenshots. And this is what I'm doing, comparing this screenshot with my target image and compute the SSIN, okay? So using, then I have segmentation, more complicated stuff. This case also, there is one design variable. We have it with 12 design variables, and it works very well, okay? And many times now, the interesting here is that it's not only about measuring that integral quantity. Sometimes, in many cases, it's better to use techniques of the image recognition just to match a field to another field. Also, right now, also we're implementing something just to have bubbles with multi-phase and to identify the bubbles using segmentations and to measure diameter automatically. So I guess at this point I have just 5 minutes. I will stop here. Let me see if I forgot something. So basically, yeah, you have these cases there, everything ready to go. If you want to use this one, I just remind you that you need to get your credentials and put it in the support files here in credentials. You need to put your credentials. Then you have this blunt body. Also, it runs out of the box. Okay, so it will use Salome. You need to have Salome 9.6. Anaconda 3 also, or Python 3, and that's all. So with that said, I think at this point I will stop, and if I have time, I will answer questions. So let me move. Okay, yeah. The Vedo, actually, I look at that, and I think I will play around, and that Vedo library, yeah, probably will solve a lot of problems, because now I don't need to use to install the ParaView. So yeah, I think 2 days ago it was you that mentioned that one. Immediately I check it, but yeah, I'm sure that it can be a good alternative. Will Onshape give you STL files that are conformal? What do you mean by conformal? That Onshape will save whatever you have in your solid model. So whatever you do in your CAD model, when you do your geometry, I don't know what is loaded, not loaded. Whatever you have in your CAD model, it will show you. So the Formula One that you see is done fully with Onshape. Yeah, for HPC, yeah, you use the Hecklet small, but honestly, these Vedo libraries, I see that is a good alternative for that, to avoid that. Then in the image processing script, it seems you manually are using. Yeah, in the script, I'm doing some crop just to have a small region, but I think it's not relevant. It's just something that, you know, when you're programming, you have some ideas there. I actually doing the cropping because sometimes I keep the scale, and that scale can affect your structural similarity index. So just to show you, so it might happen sometimes you keep the scale here. So I do the cropping just to avoid this one, but it doesn't matter. It's up to you. Okay. Also, again, the question: it's better to use white or gray or gradient. It doesn't matter because this image from RGB is converted into grayscale, so it doesn't matter what color you put. Avoid gradient, but this is white or black. It does not make any difference because you convert it to grayscale. Yeah, I think you have the links somewhere in the conference room, but also in Twitter. I tweet that the information it is available. Yeah, you can have conformal. Yes, there's no problem. So you have access to exactly same capabilities in a CAD software now. So everything that you have there, you can have it. So there is no problem. So, well, I still have 50 seconds. So if anybody else has questions, just let me know. Otherwise, thank you very much for your attention. As I mentioned, we have our websites. You have to visit, I know, Wolf Dynamics, or in Twitter, also with tweet. But you can find all this material. You have it there. Also, I will clean up the tutorials because, as you see, I realized that there were some problems. So I don't know if it were my files that I was playing around or what you have. So I will see if there are problems, but I think whatever you can download should be working out of the box, but you need to install all the same tools. Dakota 6.13, OpenFOAM 8, and Python 2 and 3. Okay, bye. Thank you very much.